Good afternoon, or morning, or evening, or wherever you're joining us from. I'm Rebecca Roberts. I'm the Deputy Director of Events at the Library of Congress. But for a long time, I was on staff at Planet Word, and I am delighted to be able to be back in the fold here to continue this wonderful series, Language And. It's an occasional series from Planet Word where we explore the intersection of language and kind of anything you can imagine, because language does in fact intersect with anything you can imagine. And the series is made possible by the Jack Joseph and Morton Mandel Foundation, and we really appreciate their support. Our guest today is Sarah Hart. Her new book is called Once Upon a Prime. You can see it in reverse there, The Wondrous Connections Between Mathematics and Literature. She is a professor of mathematics at Birkbeck University of London and the Gresham Professor of Geometry. Sarah Hart, thank you so much for being here.
Thank you. It's an honor to join you today.
So you talk at the very beginning of the book about how math and language are both ways of understanding the universe. And how are those different perspectives the same, and how do they differ if those are your lenses for understanding the universe?
Yeah, so I think I would say mathematics for me is a language because, when scientists want to describe particular phenomena that occur in nature or in the skies around us, then we might talk about it in words, but we might also use equations and mathematics to describe what's going on. So we often hear that phrase that mathematics is the language of the universe. And for me, that is absolutely what's happening. It's another language. So it's part of the same endeavor. But because mathematics describes things like structure and pattern and symmetry, of course, that's why it's useful for science, but it's also useful for understanding and exploring some of what makes language. So I suppose the similarities, because we're communicating, but both things are communicating ideas and encapsulating truths and all of that. But so that's a similarity. Difference, well, I don't know. Is there a difference? It's two sides of the same coin, perhaps. So there are some ways in which, we think perhaps of mathematics as a language that is rather precise, maybe. And sometimes we need to be very precise if we're writing down, if you're doing a calculation, you need to understand and be precise about what the numbers are that are involved. And language, different kinds of language, you might have more ambiguity, deliberately or otherwise. So that's perhaps a slight, a difference.
I also wonder if maybe you can understand both disciplines at several levels, right? That mathematics only seems rigid and hidebound if you don't get to the level where you understand how imaginative and wild it can be.
Yeah.
And that language seems chaotic and pure imagination until you get to the level where you realize the underlying structure and that you need to master those rules in order to break them and to create something truly beautiful with language. And that math is only precise and language is only imaginative is just a simplistic understanding of both.
Absolutely. Yeah, absolutely. And mathematics, even a lot of what people learn in school that is called mathematics is to actual mathematics what, spelling or something is to literature. It's a tool that you need to be able to use in order to do the thing that you really want to do, which is the mathematics, which is about pattern and structure. And it's not about what's 7 plus 6. I mean, you need to be able to know what 7 plus 6 is, but that is not really what the mathematics is. I think of numbers as that they're kind of a side effect, an artifact of what's really happening.
You say in the book, my goal in this book is to convince you not only that mathematics and literature are inextricably and fundamentally linked, but that understanding those links can enhance your enjoyment of both. And after reading your book, I absolutely understand how understanding mathematics can help me appreciate literature. How does appreciating literature help you understand math?
Yeah, well, because when you're doing mathematics, if you're going to do new and interesting mathematics, you have got to be creative and you've got to have ways to grasp and think about really challenging, difficult concepts. And the way we do that, the way humans always do this kind of thing, is with metaphor and symbolism, and language and literature. That's what gives us those things. So when we come up with a new concept in mathematics, we give it a name, and that name is evocative in some way, and it helps us to understand what's happening. So we can't just have a pure construct that's totally abstract and free of any kind of sense. And so we use metaphors and language all the time in mathematics, and it's just part of how we understand what's going on. Yeah, so it's really important.
So for instance, your field of study, which you describe as an area of abstract algebra known as group theory, what's your metaphor for describing that?
Yeah, so I think for me, it's all about symmetry. So I think of what I study is where geometry meets algebra, and in that space, there is such a lot of beauty. And I'm making a metaphor with my hands, but this is where
use whatever language you need to use, Sarah.
Mathematics. This is where it's all happening, right? Where these two concepts meet each other is where this area called group theory fits. And there are lots of if you're talking about abstract algebra with another mathematician, you have all these kind of ways of describing the structures that you see. You say this thing's on top of that, or this is we talk about braids, which are a particular kind of way that symmetries can interact with each other. So that we talk about braids and think about knotting things together, and even though that's not really what's happening, there's a lot of that kind of language that goes on. And yeah, there's so many. Every time we have a different way that things can combine, we'll pick a metaphor from somewhere else. So I like braids because I have very long hair. So there
you go. Right. Again, use what you have. So the book is divided into parts that explore this relationship, and you start with talking about literature with a structure. Whether it's something very formal like a haiku with the 575 syllable structure, or obviously there's a lot of poetic forms with a lot of structure, sonnet, anything with a predictable rhyme scheme or meter. But you broaden that out to include works of fiction that impose various structures on themselves. One example is the luminaries, and I actually see it behind your book, your bookshelf there. Tell us a little bit about why you used that as an example, because I'm sure lots of our audience have read it.
That wasn't deliberate.
It wasn't a problem.
Good. Okay, so this is the book you just mentioned, The Luminaries. So it's Eleanor Catton's Booker Prize winning amazing novel from 2013, and she was the youngest person at that time to be nominated even for the prize, and then became the youngest winner at 28. It's, as you can see, quite a substantial novel, and there's lots going on. It's got everything you could want in a plot. It's got opium and gold and death and betrayal and love and murder, all of this going on. But the key theme for me of the book is about the interplay between chance and fate, and how much we're in control of our destiny, and all of those ideas. And so she weaves into the structure of the book various links with astrology. So she's got 12 characters who are associated to the 12 signs of the zodiac, and to some extent their actions at any point are determined by where the stars were in the night sky at the time the events are set. So this is sort of saying it's a way for her to have enforce some control over those characters' actions when they think they're acting freely. But there's also two main characters, the luminaries of the title, the sun and the moon, who are the lovers. And to kind of tie in with all of that, there are 12, the book is divided into 12 kind of sections or chapters. So 12 because of the 12 signs of the zodiac. And to mirror the waning of the moon, the chapter lengths have a very specific mathematical structure, which is that every chapter is half the length, exactly half the length of the one before, so it's sort of like the waning of the moon. And when you're reading this book, the effect that it has on you is that you start to feel kind of the pace is quickening, and kind of the things are turning in on, spiraling in on these two main characters, and their fate is kind of being sealed around them as these chapters decrease and decrease and decrease and decrease in length until the very final chapter, which is very short, necessarily so because of this sort of halving and halving property. It's just a conversation between those two characters. I just saw in the chat someone's asking the name of the novel, The Luminaries by Eleanor Catton. So it's you feel it happening, you experience this structure as you read the book. The chapter shortening really has a strong effect on your experience of the book. Mathematically, though, it's really a very, very powerful restriction, this constraint. She's chosen to do this halving and halving, and that means, I won't like do a page of algebra right now, but it's not too difficult to work out, if we had a few minutes to do this, that the very last chapter really determines everything else about the length, because the penultimate chapter is then twice that length and 4 times and 8 times and doubling. If you do all the doublings, you find the first chapter is more than 2,000 times as long as the last one, right? So you've got to have really precise control over how the length of that shortest chapter, because you've got to multiply that by over 2,048 to get to the first chapter. And you can also, there's a very nice mathematical formula to work out the total length of the book, because if you add up 1 plus 2 plus 4 plus 8 plus 16 and so on, add up the powers of 2, there's a lovely, very short little mathematical proof that you can do that says the sum of all of those is the next power of 2 take away 1. So if you add up all of these chapter lengths, you can work out exactly the length that the book is going to have to be in terms of that shortest one. And it turns out it's 2 to the power 12 minus 1 multiplied by this shortest length. So the reason I've said that in detail is because you might be sitting there thinking, well, Sarah, you're a mathematician and you're sort of looking at this and you're doing your own little maths for your own, pleasure, which is fine. But Eleanor Catton maybe wasn't thinking about any of this stuff. She just chose this structure because it fits in nicely with the book. But she's not thinking about 2 to the 12 or whatever, anything of that. However, in the book, there's some stolen gold, and there's a court case, and everyone's trying to work out who has stolen the gold and what's happened to it. And the amount of gold, the monetary value, is stated in the book, and it's £4,096. And that's 2 to the power 12. Okay, so that is her. I think she's giving us a little present, but she's also saying, yes, I do know, and this is my conscious choice. I have, that stolen gold, it's kind of sewn into the fabric of the book. It's just a really lovely little thing that she does there to show us, yes, she does know what's going on. She has chosen this consciously and she's exploiting it all the way through. So yeah, sorry, long answer to your question, but yeah.
No, I love it because, I think that sense that you describe as the chapters wane, and the inevitability of the ending starts to sort of close in on the characters. I think you feel that happening as a reader, even if you're not clocking the word count, right? And I certainly didn't get the gold reference. I didn't know that Eleanor Catton had checked out the astrological positions at the time of the story, to make sure that she was to some degree accurately representing that. But I did feel the effect of the constraint. And so to me, it felt like it added to the story. I must say, when I, for instance, read a poem that is all words without the letter E or something like that, my first thought is, think what a great poem this person could have written if they used E's, right? So, and you actually bring that up. You said in it, you may be thinking, and I was, why would a writer bother with some fancy structure? Why not just write a good story? This, I would argue, is a false dichotomy. Why is it a false dichotomy?
Yeah, so because whatever you choose to do, however you choose to create your work of literature, you are making choices at every level. So if you think of how a piece of language is made up, so at the level of a book, you might divide it into chapters or not. And those chapters might be divided into paragraphs or not. Paragraphs are made up of sentences. Sentences are made up of words, words of letters. And at each stage of that, the author can make a decision about whether they're going to do anything, how they're going to put this together. Some books, don't have line breaks, they don't have chapters, some do. Some, as you say, at the level of the letters, there are some books or pieces of writing called lipograms that omit certain letters for whatever reason. So I would argue it's not about whether there's structure, it's about what structure you choose. And so that's at some point, that it isn't a choice between structure or no structure. It's a choice of what structure you're going to impose. And actually, these decisions about, if I'm writing a poem, what kind of poem will it be? Will it involve line breaks? Will it involve rhyming? Those decisions themselves do not determine whether a thing is great literature or great art. You can write a terrible sonnet and you can write an amazing sonnet. So I think that what mathematics can do for you is to give you kinds that can help you to find structures. And then within those structures, you can play and explore what is possible. And you can do that in literature, but that's exactly what we do in mathematics as well. We set up ground rules for ourselves. We might have geometry, the kind of geometry we all learnt at school, angles in a triangle add up to 180 degrees, that kind of thing. That is based on a few ground rules, axioms of geometry that kind of set up by Euclid a couple of thousand years ago. Within those rules, we can prove Pythagoras' theorem. We can prove lots of lovely things. But if you change the rules slightly, you can get different kinds of geometry and prove different very interesting things. So it's all about setting up a structure and then seeing what we can make with it. The structure itself is not good or bad. It's what you do with it.
Yeah, although a lack of structure can be bad.
Yeah,
I think we've all had that very unsatisfactory reading experience where you feel like nothing was resolved.
Absolutely. Yeah. There's a sweet spot, I think. And this, again, is the same with mathematics. If you impose too much structure, that you can't do anything interesting. If you don't have anything at all, there's nothing to go on, and you're just
there's no there. Yeah.
Yeah.
Another section of the book talks about numbers in stories, and I found this fascinating because certainly there are numbers that recur a lot, especially in Western tradition. The three pigs, the three bears, seven also, and you call these magic numbers.
Yes.
And at first, as I was following along, I was like, oh, they're prime, they're interesting. But then 12 and 40 got in there. So why do you think certain numbers are magic or favorite or recurring, are particularly resonant in stories?
So I'm going to say there are three types of number. Already I'm using the number 3 because we seem to enjoy dividing things into 3 quite a lot. So sort of special, these magic numbers that you get in fairy tales and folk tales, if they're small, things like 3 crops up a lot, 7 crops up a lot. I mean, in Native American tradition, 4 is a very favored number, maybe to do with the points of the compass. But there are all sorts of reasons why those particular numbers might be favored. As you get bigger, then you get to, at the other extreme, sometimes you want to express in writing a very, very big number. Sort of generically big number. Nothing, no, you don't know exactly what it is. So if you're going to do that, you're quite often, and this is a mixture between a mathematical and a biological reason, right? Here is the reason 10 is important. There's nothing special in that way about the number 10, except that we have 10 fingers, and so we tend to count in tens. If we were, a different species with 8 fingers, we might have 8s and 64s and powers of 8. Well, our decimal system is based on powers of 10 because of our biology. But once you have got the 10 from kind of biology, powers of 10, 100, 1,000, 100,000, a million, these very big numbers sort of stand in for large. So if in Ireland, you traditionally are greeted with 100,000 welcomes. I think in China, you maybe wished 100 more birthdays. These big numbers are signified by powers of 10. But then there's a way that can be tweaked. And that's the sort of second thing that can happen, is that you might want to say, this is so big, it's even bigger than big. So you might have to tell stories for 1,001 Arabian Nights. It's even more than a really big thing. Or you might perhaps not quite get to the great big number. So that can be represented by numbers like 9 and 99 and 999, which are almost a big number, but not quite. So I think in some parts of the Islamic tradition, there are 99 names of God that are known, and then there's sort of one final 100th name, which is mysterious. So the kind of the not quite getting to the big number can happen, your 99s, and then you can slightly exceed it to your 1,001s. But then with the smaller numbers, like 3 and 5 and 7, quite often those are small prime numbers, and prime numbers have a sort of strength to them because you can't break them up in any way. And so if you're making some kind of structural pattern, if you have 7, it's not ambiguous. You know, if it were 8, it could be broken up as 2 4s or something like that. Whereas a 7, it's very strong. You can't do anything with that. So it has a sort of power to it, which is, I think, part of the reason why 7 occurs so often. But then there are other little things. So potentially adding to that mathematical reason why 7 is quite prevalent is a reason that is very much related to astronomy, which is before telescopes or anything like that. You had the stars that were far off twinkling away in the sky that didn't seem to move, but then you had 7 heavenly bodies that moved in the sky. So the sun, the moon, and the 5 planets that we could see before telescopes came along. And so those gave a special significance and that were important. So these 7 important wandering stars perhaps then gave a reason to why 7 might have been astronomically significant. And perhaps that's why we have 7 days in the week. And then once you've got 7 days in the week, lots of other things kind of hang on to that as well. So quite often there's a really interesting mixture between the mathematical reason and then some other reason, which might be to do with our biology or something about the sky, the astronomy that we see around us. 40 is another one. So 40 is it feels anomalous, right? Because it's not a small number, it's not a big power of 10. So what on earth is it doing there? Well, actually 40 quite often represents, in the Bible and other holy books, some sort of period of waiting, and then there's a big change. So various people will go into the desert for 40 days and 40 nights, right? In ancient religious stories. And for me, that number 40, it's a round number, it's 10 times something. It also can be divided up in lots of different ways, so that maybe if you can break it up and make it in different ways. But for me, 40, I as a woman have counted to 40 very carefully twice in my life because I've got 2 children and pregnancy lasts 40 weeks. So, that again, that's a very important number for us as a species, let's say. So there are all these different reasons. But yeah, 3, probably the most prevalent in kind of, and in Western culture and in kind of the English language. Lots of idioms with 3 in, we learn our ABCs, we don't learn our ABCDs. When we want to congratulate someone, we give them 3 cheers, not 2 cheers. When we run a race, we say ready, set, go, 3 words. At the end, it's the top 3 people who get medals, bronze, silver, and gold. There's all of these things that they don't have to be 3s, but they are 3s in our idiom. And politicians love the 3-word slogan as well. My lips. No new taxes, you might remember that. So yeah, it's really, once you start looking for 3s, I guarantee you'll see them everywhere. And they're everywhere in narrative as well.
It's the rhythm of a well-told joke too, right? Da-da-dun, da-da-dun, da-da-dun. Yeah,
exactly. Yeah, and that narrative thing of the joke where, so in a joke structure, it'll be some situation that there might be 3 people who are presented with the situation, and kind of the first 2 people react in a normal way, and then the third one does something ridiculous, and insert your cultural stereotype of choice for whoever the third one is. And this happens in fairy tales as well. You have three brothers going on a quest. The first two will fail because they're arrogant, or think they're clever and they're not. Then the overlooked youngest brother comes along and succeeds. Now, in each of those cases, what's happening is it's really a mathematical thing. For me, it's that, okay, if you have one thing happen, the first thing happens, it's just an isolated data point. Then second event, now you can draw a line. You can make an expectation. And so then you've got an expectation which the third brother, data point, person in the joke can subvert and go up here. So 3 is it's in geometry, it's the smallest number of points you can draw to actually make a shape, a triangle. Otherwise you'd get a line, just a boring old line. You kind of go up a dimension with the number 3. And then in narrative, it's the smallest number of events you can have to have first created an expectation and then subverted it. So it just, that is what's going on with 3 in narrative. Yeah.
Fascinating. You talk about writers who use a lot of math in their narrative, mathematical metaphors, mathematical characters. And the first writer that sort of opened your eyes to this was Herman Melville in Moby-Dick. What was it about Melville and math? Why was he so interested?
Yeah, well, I mean, of course he was interested, because math is interesting.
Endlessly fascinating.
Obviously, yeah. So for me, this was, I'm lifelong reader, obsessed with reading, but always a huge part of my life, and I'm a mathematician. And so somehow I'd been seeing things, but not necessarily being consciously thinking about them. I'd just sort of say, oh, that's nice. But really, Moby-Dick was the book that got me really thinking carefully and extensively about mathematics and literature. So a friend happened to mention to me that Herman Melville in Moby-Dick has a passage about a mathematical curve that we both liked, called a cycloid. So I like cycloids, but mathematicians know what they are, but most, the sort of general member of the public doesn't necessarily know what a cycloid is. So I was intrigued that this curve would get a mention in Moby-Dick. And it was one of those books that it was on the I ought to have read this list, those, and then you don't want to because you think, I'm not doing my homework, I'm not going to read this book. So anyway, this was the prompt that thank goodness, that got me to read Moby-Dick. And of course I loved it because it's amazing. But right from the start, it was clear to me that Melville enjoys mathematics, because really from the first few pages, he would use mathematical metaphors. He's got this, even at the very first part of the book. So he stays at the Spouter Inn, if you remember, and it's a kind of grimy, horrible little inn. And the landlord serves him a drink, and he describes that it's in this cylinder with parallel meridians marked on the side, and I was like, oh, cylinder, oh, parallel meridian, these are kind of, it's a quite geometrical metaphor. And as I carried on reading, there are more of these things. So it feels as if for Melville, mathematics is part of the furniture of his mind. It's there. And of course, any writer, if you want a bit of imagery or symbolism, you reach into your mind and you find something. So I don't think he's thinking, right, I'm now going to do a mathematical metaphor. It's there, and it comes to his mind, and that's how he chooses to express things quite often, and much more often than I, would have seen in many other books. So he clearly enjoys mathematics, and his understanding, his level of mathematical knowledge is surprisingly high, actually, because so there is this lovely passage about a curve, the cycloid, which is a lovely curve. It's the curve you get if you imagine a wheel rolling along a road, and then just follow what one point on the rim of that wheel does as it rolls along. And as the wheel rolls, this point will make a sort of arch-like curve. And that's what a cycloid is. So it's a kind of natural idea. Galileo studied it. He was the one who gave it the name cycloid. And then all these other mathematicians studied it and found it fascinating and beautiful. So Descartes, Fermat, Isaac Newton, like anyone you can think of in the 17th and 18th century studied this curve. It's got loads of brilliant properties. And Ishmael talks about one of these properties, just almost as an aside. He mentions this. And it really intrigued me because this is not something you learn at school. And I thought, well, maybe that you did in 1850. No, not usually. This is not, it's not in, the books of Euclid, which were the kind of, that's what you would learn geometry from at that time. It wasn't in the other traditional mathematics textbooks that were tended to be used in America at that time, which I sort of had a look into. So how does he know this? And this led to a little detective trail. And I found that a researcher called Meredith Farmer had looked into actually what mathematics education Herman Melville had had. And he'd gone to this school called the Albany Academy in 1830 and 1831. And he'd had a teacher who was such a great teacher of mathematics that some of his lessons were actually made open to the public to go along and attend the lesson. So this teacher, there's record of him applying to the board of governors to say, can I teach them some more advanced things, and can I look at different books to get them. Melville was in the top of his class. He won prizes for mathematics. There's one prize he won for mathematics that was a book of poetry that I really liked. But of course, right. What a great gift for a mathematician, a book of poetry. Absolutely. So anyway, this teacher was a man called Joseph Henry, who actually is well known, remembered now. He was the first secretary of the Smithsonian. Henry, that surname, the Henry is now the official unit of inductance, which is a physical unit measuring inductance in physics. So he's like a well-known and respected scientist who happened to be Herman Melville's mathematics teacher when he was at school. So that's like, we can't prove that he taught him about cycloids, but
it's a great story.
Yeah.
Well, also for those of you in the audience who live in Washington, if you've been to the Smithsonian Natural History Museum, the big elephant that greets you when you walked in is Henry, named after Joseph Henry. So
oh, fantastic.
Joseph Henry is very much commemorated here in town.
Excellent.
Another writer who uses a lot of mathematical metaphors is Leo Tolstoy. And especially in War and Peace, there's this extended metaphor of history as calculus. Explain that for us.
Yeah, so that's another lovely thing to find that. So calculus is this amazing mathematical discovery, I guess, that Isaac Newton and also Gottfried Leibniz independently discovered, and it helps you to understand processes or things where, and you've got movement, and you have movement that happens kind of continuously. So you can't just it's not a situation where you can add up discrete separate little amounts. You've got to find a way to understand the mathematics of the continuum in this way. And the invention or the discovery of calculus allowed Isaac Newton to do things like explain how gravity makes the planets move around the sun in ellipses, all of that. So it's a really, really powerful tool. So what's Tolstoy going to say about it in War and Peace suddenly? Well, that there are some fun mathematical references in War and Peace, but this is the most exciting for me. So he's very interested in thinking about how we can understand human history, like as it unfolds. And for obvious reasons, he's not a great fan of thinking Napoleon's wonderful and he caused all of this, everything to happen. What he says is it's not an individual person ever that causes events to happen. Napoleon is not the cause of these things. He's almost like a side effect of a great movement of history. It wasn't Napoleon, it was history itself in its movements, which are bigger than any one person. And so he says, if we're going to understand history, we've got to do the same thing that mathematicians do with calculus. We can't just look at individuals. We have to understand the whole of history is working together by kind of not adding up one or two individuals, but adding up the contributions of every single human being. In order to do that, we kind of have to move from these individual points to a continuous the continuum of history. And to do that, we have to have some sort of calculus of history. So that's what Tolstoy is saying. Just like Newton, and others developed calculus to be able to turn from the discrete, the separate, to the continuous, we have to do the same thing for history. So it's a really interesting discussion.
It really is. And it's so contemporary in so many ways. I think there's definitely a conversation being had here in the US about sort of rethinking the great man Hall of Fame model of history and, rethinking what it does mean to be an agent of social change and who gets to make history and movements as opposed to, the heroics of one individual. And that's exactly Tolstoy's point. It's fascinating.
Yeah, absolutely.
You also talk, and I love this part in the book, about writers who use characters who are mathematicians. And often, too often, probably in your view, they are sort of stand-ins for rigidity or, kind of a synecdoche for someone who follows the rules or, without necessarily being able to imagine a different outcome. How do you have a favorite mathematician in literature? Do you wish people would write them a different way?
So I think, there are tropes that get used repeatedly that are, of course, when you are reading a book, you prefer your characters to be three-dimensional than not. So there are certainly, you find, and this happens. There is brilliant science fiction writing out there. I love science fiction, but the not great end of the scale will have a mathematician type character that is just there to allow something to occur. They invent the quantum hyper transmogrifier.
You call it performative arithmetic, which is
exactly this magic thing comes in, and then the mathematician's job is done. So that's not brilliant. There are, even in kind of really interesting books like Asimov's Foundation novels, he is a man of ideas. He isn't necessarily a man of amazing characterization. I hope I don't want to offend any Asimov fans, but that's not why I read Asimov, right? I read it because he has some brilliant ideas. So he's got this character, Harry Seldon, who invents a kind of mathematical way to predict the future. And he does that, but he's a being of pure logic. And so, can you hear the rain?
A little bit. Yeah.
Let happen. He comes up with this mathematical theory, and it allows you to predict the future, but he doesn't. That's kind of all there is. So it's a very interesting idea and fun to follow. But as a person, as a character, not super interesting. You've got the other kind of mathematician in books, which is the tragic genius, the child prodigy who is driven mad by their genius. Again, that's less appealing, perhaps. Sometimes it's gone well. I think that the characters I like, and of course, are the ones that are human beings who are also mathematicians. So you get, for instance, the Mark Haddon's book, The Curious Incident of the Dog in the Nighttime, which is about this young man who he's never quite specified, but he's got this sort of probably somewhere on the autism spectrum, and he really enjoys mathematics, and he does things in the book like he decides he's writing this book and he says, I'm going to not number the chapters 1, 2, 3, 4, 5. I'm going to number them 2, 3, 5, 7, 11, and so on, because those are the prime numbers, and I like the prime numbers, and it's my book, so I'm going to. But he's got this lovely description of prime numbers, and his enthusiasm and joy in mathematics is really infectious, but it's not, he isn't a stereotype. So he's not a stereotype of someone with autism. He's not a stereotype of a mathematician. He's a wonderful, brilliant character who you really empathize with and love. So that he's a brilliant character. And one other one I'll mention, and there are some real mathematicians who are portrayed in literature as well, but a fictitious mathematician is the character of Odenigbo in Half of the Yellow Sun by Chimamanda Ngozi Adichie. And this is her wonderful novel about the Nigerian Biafran War. And it tells the story of that war through the eyes of a group of characters who get caught up in it. And one of them is Odenibo. He's a professor of statistics at Nsuka University. And that's, so there is something about the mathematics that he's interested in and does, but also he does all sorts of things. He's good, but he's also bad. He's flawed. He makes mistakes. All of those things make him a fully rounded individual. And so I love him. I'm going to get my headphones because of the massive thunderstorm that's decided to happen.
And in fact, somebody in the chat mentions the mathematician in Tom Stoppard's Arcadia as so compassionate. And you bring that character up in the book.
Yeah. Thomasina, she is so amazing. She's just brilliant. So this is a play. Tom Stoppard, he is brilliant at writing about mathematics and about science more generally. He's in Arcadia. It's a wonderful play. It's set in about 1809 and also roughly the present day. In 1809, Thomasina Coverley is this kind of young noble woman. She lives in a big country house. She is a child prodigy, but not the tragic kind. She's the exuberant, happy kind who's got full of ideas, and she wants to explore all of them. They have this wonderful discussion about Fermat's last theorem, which of course is a very famous thing, often badly dealt with in literature because people will say, their little genius that they have will find the very short proof of this theorem that was sought after for many centuries by mathematicians. In this play, there's a discussion of it, which is really, very mathematically astute. There's also ideas about fractals and chaos theory and all sorts of things going on. But Thomasina is just a delight. She's just happy and, intelligent and funny and good at mathematics. And, she's a lovely, lovely character.
You mentioned fractals, and you bring that up in the book in the context that, literature regularly reflects trends and things that people are talking about. And the same is true of the math in books. And, there was a whole obsession with the fourth dimension for a while. Fractals became very much a part of literature in the Jurassic Park
Yes,
era.
yeah.
Are there trends you see coming up? What do you think we're going to start seeing reflected in literature?
Yeah, so I think, topics around, well, a few years ago we called big data, but now it's all linked in with the kind of ChatGPT, large language models, the mathematics around that, I think, which is obviously linked with AI and all of these themes and ideas. That's quite a hot topic, I think. Another one is, cryptography does occur already. There are books since Edgar Allan Poe that there have been things that deal with cryptography, but I think now we've got the idea of perhaps quantum cryptography, which is where all the codes that we use at the moment, the encryption methods now that many of them involve actually quite old mathematics, because it's the mathematics of prime numbers that at the moment these things are essentially uncrackable because of the mathematical properties of prime numbers. But if quantum computers can be created that are big enough, suddenly these things will be able to be cracked. And so we need new methods, and the mathematics around that is, I think, there will be buzzwords. So what tends to happen is you get some buzzwords like, I don't know, elliptic curves, right? They're a thing in mathematics. I bet you, if it hasn't happened already, elliptic curves will be this topic of some, spy thriller or, thriller where someone's racing against time to crack the elliptic curve. That's my prediction.
All right, you heard it here first. I want to get to the audience Q&A, so please put those questions in the Q&A box. But first, I want to ask you a little bit about your job, because reading your bio on the back of the book jacket, it says she's a professor of mathematics at Birkbeck University, London. I think we all can understand what that is. Dr. Hart is also the 33rd Gresham Professor of Geometry, the first woman to hold that position since its inception in 1597. So I think certainly as an American, you're like, she has a tutor job. What is going on? But also, what is the Gresham Professor of Geometry?
Yeah, so in 1597, Sir Thomas Gresham, who was a Elizabethan financier, he founded the Stock Exchange in London. He worked for Elizabeth I. He became quite wealthy because of that. And when he died, in his will, he said, I want my money to be used to found a college, which is Gresham College. And the purpose of its existence is to provide free public lectures to the people of London, to anyone who wants to come along. And so he provided for, if we think what of the 7 traditional liberal arts of antiquity, which is, I have to get them right, but
there's that number 7 again. Right?
7. So you got, rhetoric, logic, grammar, geometry, astronomy, music, and another one. Someone will tell me geometry, astronomy, music. Okay, and so he set up these 7 professorships, and geometry is one of them in 1597, and they still exist. And the role is still give free public lectures to the people. Well, not just in London now, of course, because we live stream them all and anyone can watch them forever on YouTube. One thing has changed. Thankfully, you don't any longer have to give each lecture twice, once in English and once in Latin.
Oh,
which
phew.
was the original requirement. So I only have to give each lecture in English, which is probably for the best for everybody. But yeah, it's, I mean, of course, because I like communicating about mathematics. This is a dream thing for me to be able to do, and the lineage, of course, is just I feel so privileged to be part of that this lineage that goes back kind of 430 years, and to be part of that line of people, and people who've held these roles. So Robert Hooke, who people might remember from school, Hooke's law, which tells you about strings and springs that stretch. So he was a Gresham Professor of Geometry some years before me. Christopher Wren, who designed St Paul's Cathedral, he was actually a Gresham Professor of Astronomy. So they're just these kind of, wow, it's a huge privilege to be in that group of people. And I remember actually when so Jordan Ellenberg reviewed my book in the New York Times, and he said the first person to hold my job invented long division. So it's like that's quite a thing, isn't it? Yeah. It just kind of makes you really feel that's a long time ago.
We have a couple of great questions coming up. Renee asks, as a mathematician who is also an avid reader, it sounds like you think, and she is think in quotations, of math in verbal language. Temple Grandin famously talks about thinking in pictures. Do you find there are divergent ways to approach math among your colleagues?
Absolutely, yes. There definitely are, and you can see it happen. There'll be the person. Actually, I'm this person. There can be a thought in my head, and it's almost like trying to, if you hear a chord of music or something, the attempt to crystallize it into individual notes causes you to not be able to hear it anymore, and it takes a lot of skill or practice to be able to write that down. You can have that in mathematics too, where you've got what's happening inside your brain, and then for me, I have to draw a picture. I have to write something down, but I will draw a picture. It's not like a picture, it'll more like be some connections. So I might just write a few things and then link them together with lines. That's the kind of picture I mean. Then I can turn it into symbols, but mostly it's a picture actually that comes in, and the words come later. But that's true, I think, of lots of thoughts. You might have a particular image in your mind, and then there's a process of turning that into words. But I don't, the words are not necessarily the first thing, and neither are mathematical symbols the first thing, actually. So yeah, I don't know. Maybe it's an autism thing. I don't know.
Jeff Shearer asks, some authors see time as a human construct. Have you seen examples where an author uses mathematics to make past and present a fluid view of time, as opposed to sequential periods of time?
I'm not sure I quite know what I'm not sure I quite know what you're asking there. But I mean, certainly there are authors who play with the idea of time and link it in with the fourth dimension as well. Thinking of Kurt Vonnegut when he writes about Billy Pilgrim who gets stuck in time, unstuck in time, and that is described by thinking about the fourth dimension, which is where, you know, we see things. We know that there are three dimensions and people exist in three dimensions, but actually, if you think everybody is a shape, has some existence in four dimensions, if the fourth dimension is time. And so the aliens with whom he is talking, the Tralfamadorians, they see the whole of a person's duration as well as their height, you know, their three-dimensional physicality. So if you're doing that, then somehow you can see every point in time at the same moment. We might need a different word for that because in the fourth dimension, if you are able to see that fourth dimension, then you precisely are seeing all points in time at the same moment. Yeah, but I'm not entirely sure if that was the question, but that's a question.
No, right. And it playing around with dimensionality, somebody in the chat asked, do people still read Flatland? And actually, there's a whole chapter in your book that's more or less a love letter to Flatland, which you introduced me to. So introduce the rest of us to Flatland and explain.
Yeah. So Flatland was written in the 1880s by Edwin Abbott, who was a school teacher. He was a head teacher of a boys' school in London, and he was a Church of England priest. And so he wrote books about theology, and he wrote Latin primers and things. And then in the middle of that, suddenly, Flatland, a romance of many dimensions. And it's about this world. It's a two-dimensional world whose inhabitants are shapes. So triangles, squares, pentagons, those kind of things. Well, that's the men. The women are lines. So they're a dimension below. Now, I want to defend Abbott before we go any further, because this book is a satire on Victorian values, of which he does not approve of many of them. So he doesn't like that women don't have the opportunity to get educated in the same way as men. He doesn't like that disparity. He would like women to have more freedoms, and so he's taken this to the extreme in his imagined society by making like the women are lines and only the men are actually full shapes. So there's a bit of that, and kind of swipes at various aspects of the way the Victorians deal with religion and all of this. But then in the second part of the book, he goes into this kind of allegory of dimensions. So he imagines a visitor from Spaceland, which is a three-dimensional world, and this visitor comes to the Flatland, two-dimensional world, and sort of introduces the main character, whose name is Square, because he's a square, to the idea of three dimensions. And he initially doesn't believe it. He won't believe it. Because he can see just where this sphere meets his two-dimensional world. He sees a circle. He said, yeah, I don't believe it. None of this is true. Eventually he gets convinced, and then he goes back and tries to explain to his friends and colleagues, look, there are there's the higher dimensions, and they won't believe him. But then he says to Sphere, great, can you take me to the four-dimensional world? And Sphere says, how ridiculous, how dare you speak such blasphemy, and, you know, disappears forever. So of course we then we've thought Square is silly for not believing in three dimensions, and then we're inexorably led to think perhaps we would be silly if we didn't believe in four dimensions. So he introduces the concept of the fourth dimension, which was a big new thing in the 19th century. But Flatland itself has had a huge influence. So there have been sequels, there have been other kinds of ways of other people have invented different two-dimensional worlds. Somebody invented a world, Sphereland, where it's still kind of two-dimensional, but the characters discover that they're actually living on the surface of a sphere. So it's a different kind of two-dimensional world. So there's all sorts of sequels and spin-offs and inspirations from this one book, which is, yeah, really entertaining read.
Yeah, someone in the chat says their 7th grade math teacher used to read it to them in class.
Okay.
So we are almost out of time, but I want to ask you about something that a previous guest asked me about, and we were talking about language and numbers, and it was specifically about the names of numbers and how different cultural movements have named numbers and what that reflects about their culture. And he posed this sort of chicken and egg dilemma of, do you think there are more words or are there more numbers? Because of course, numbers are infinite, but there's a name for each of those numbers. So in terms of it, I don't think there's actually an answer, but it makes you kind of think about how many possibilities there are in both language and math, and how the scope can be so overwhelming as to be almost paralyzing, and ways to kind of bring that down into a way that feels like you can get a handle on it.
Yeah, the way probably we do it in language as well as in mathematics is we break it up into smaller parts. So just thinking of the words for words, and it depends on your language and on the kind of probably the development historically of your language as well. And there are these curious fossil records in names for numbers. If you think of the French word for 99, right? It's 99, right? 80 means 4 20s. 19 means 10 and 9. So actually what 99 is in French is 4 20s and a 10 and a 9. And that, of course, you don't think about that when you're actually saying it. But if you just pause and actually, so this tells us, and there's other evidence for this, that once upon a time, in old French, 20 was a unit as well. You might count in 20s. There are still vestiges of this. It's a bit in English there as well. So what you've done there is you haven't made a new name exactly for 99. You've bolted together concepts you already had. And we do this in mathematics all the time. We do it in language as well. We make words. I mean, of course, in German, the compound word can get very, very long, but we do it when we that's what metaphors do. I mean, the word metaphor itself is almost a metaphor, that we bolt together concepts, we compare things to other things. So we've always kind of starting from the sphere of knowledge that we have, and then adding on to it a bit by using things we already know. So that's how it's not overwhelming, I think.
Well, Sarah Hart, it has been a delight to spend the last hour with you. The book is called Once Upon a Prime, The Wondrous Connections Between Mathematics and Literature. Thank you so much for being here.
Thank you. It's been a joy. Thank you.
And thank you to the audience. If you haven't had a chance to visit Planet Word in person, please do. They're at the corner of 13th and K in downtown Washington, D.C. And if you are not in town or can't get here, please go to planetwordmuseum.org and check out all the wonderful virtual programs they have coming up. Thank you so much.